Welcome to Acme's Software Works, where the craft of software engineering is practiced.
In this video, we will be exploring the counting sort algorithm. Counting sort is a non-comparative, integer-based sorting algorithm that works well when you have a limited range of integers in the data. It is most efficient when sorting a collection of integers within a small range. The range of the data is in direct proportion to the amount of memory needed. Its efficiency is because it doesn't involve any element comparisons. The algorithm works by counting the frequency of each element in the data and using that information to place the elements in the correct sorted order. Each element's value is its index in the counting array. The element at that index in the counting array is used to record the frequency of that input element, and then by cumulating the counts by adding each element to its adjacent higher element. The elements now are indices to the output array, which then can be used by traversing the input array to place the element's sorted location in the output.
The implementation of the counting sort algorithm contains 6 loops. The first loop determines the range of input elements. In this simulation we will assume 0 as the low end of the range, so the loop will simply look for the maximum element. The second loop simply zeroes out the count array. The third loop traverses the input array and counts each element and stores it in the count array. Then the fourth loop cumulates the counts by adding each element to its adjacent higher element. The fifth loop traverses the input array and by using the input element as an index into the count array, determines the sorted location in the output array. Then decrements the count element, which is the next occurrence of the input element's location in the output array. And then the last loop moves the sorted data back to the original input array. During the simulation, the current state of the input array is displayed here. Unsorted elements will be red while sorted are blue. This applies to the graph as well, and the current state of variables and the count and output arrays is displayed here. Below the arrays will be an arrow indicating the location of indexes.
Now let's start the simulation and watch it unfold. First, determine the range of the input data. Remember, in this simulation 0 is assumed to be the minimum element. In other implementation, the minimum element could be any integer, including negative values. Now that the range have been determined, the count array's size will be the maximum element value plus 1. Note the plus 1 is to accommodate the 0 value. The size of the count array must have an element for all possible input values. In implementation where the minimum value is something other than 0, the size of the count array is the number of values between the minimum and maximum values. Now that the count array has been allocated, it will be zeroed out to prepare for counting elements. In the third loop, the number of each value in the input array is counted. In sorting implementations which remove duplicate values, this and the next loop are not necessary. It should also be noted that the counting sort is a stable sorting algorithm, meaning that it maintains the relative order of equal elements in the sorted output. The fourth loop is the accumulation phase. Each value in the count array is added to its adjacent larger value. This determines the correct positions of each element in the sorted output. The fifth loop is where the sorting takes place. It's a bit difficult to see, due to the level of indirection. First, the loop traverses the input array in reverse order, starting at the last element and ending at the first. It uses the value of the element in the input array as an index to the count array. That element's value -1 is the index in the output array where the input element is placed. Note that the -1 is to accommodate the 0 offset to the array. Then it decrements the value in the count array, which will be the index in the output array of the next occurrence of the same value. Because the elements in the input array were needed in their original state, in the previous loop, the sorted data was placed in a separate output array. It will now be moved into the original input array, so the calling code can have access.
The counting sort's big O is n plus k, where n is the number of elements in the input array and k is the range of values.
Please like and subscribe. And thank you for watching.